Hello guys, good evening. Hello guys, good evening. Please type in your name who are all there. So all of you, please type in your name who all are there. Hamsini, what happened? Are you better now? I saw your message. I could not reply. Who is this Roman Reigns? Aditya. Okay. WWE fan. Okay. So tell me guys what we did last class. We have started coordination compound, I guess, right? And probably we finished this effective atomic number, right? Effective atomic number, the condition of dimerization that we also have seen. Yes. Can we start? Let me know if you are there. Okay. Right. So you see, last class we have discussed about coordination compound. What is coordination compound? And then the different ligands, the terms involves in coordination compounds. Right, ligands, different types of ligands based on charge, based on density of that ligand, and then when the bonding of ligands takes place, it is because of the tendency to gain the next higher noble gas configuration. Correct. So, but that is only true, like I said in the last class, the this kind of bonding in which the metal atoms tends to gain the next higher noble gas configuration is true only for the metals which has low oxidation state and carbonyl group as the ligand if it is present. Okay, so like this is one particular rule we have, and that rule is Sedgwick EAN rule, right? That we have discussed last class. Okay, Sedgwick EAN rule. Few examples also I have seen: the reducing property, oxidizing property, and the dimerization of MCO5. All these things we have discussed. Okay, so apart from this particular bonding rule, we have other bondings also, like we have Werner coordination theory, valence bond theory, and then crystal field splitting theory. Okay, all those things we'll discuss later on, but before going into all those, first of all, we need to understand the nomenclature of coordination compound. So, heading you write down nomenclature of coordination compound. Nomenclature of coordination compound. First of all, the basic nomenclature you must have the idea. We have also the similar thing here, but since we have a term called ligand present into this, so nomenclature of ligand we have to understand. Okay, hello Samikta, right? So for that, we have certain rules, like nomenclature you must have done in organic chemistry. We have certain rules, and that we are following to write down the name of the various organic compounds. Similarly, here also for the nomenclature of coordination compound, Again, we have certain rules. Okay, so the first rule, or the rules we have to follow to write down the name of coordination compound, we are going to see first, and then we'll see some examples into it. Okay, so first rule, we copy it down. Okay, the name of the cation is written first is written first is written first always, followed by followed by sorry written first. Oh, just a second. The name of the cation is written first always, and then we'll write the name of anion, just like simple salt, just like the name of simple salt, like sodium chloride. Okay, NaCl. What do you write? Sodium chloride. So Na plus sodium will write first, and then the anion, which is Cl minus. That's what the simple thing. Now, the important thing here you have to understand is the nomenclature of ligands. Okay, so write down the ligands should be named first. Ligand should be named first within a complex. Within a complex ion, followed by the name of metals, right? Like within the complex, we'll have obviously metal and ligands present. Okay, so we'll write the name of ligand first and then metals. If you have multiple ligands, then we'll write the name in alphabetical sequence. Okay, that's what we'll see. So the important thing here we have to understand is how to write down the name of ligands. So within this second point, write down naming of ligands. First point A here, anionic ligands, negative charge. Anionic means negative charge. Anionic ligands ending with ide, ite, ate, ide, ite, ate are named are named by replacing ido, ito, and ato respectively. Okay, ido, ito, ato respectively. Correct. So the if we have sulfide, then the name of ligands will write sulfido. If it is nitrite, we'll write nitrato. If it is sulfate, we'll write sulfato. Nitrate, we'll write nitrato. So we have to write down the name of anionic ligands like this. Ite becomes ite, right? Ide becomes ido, ite becomes ito, ate becomes ato. Like this we write anionic ligands. For example, you see, suppose we have chloride ion, right? And this again you have to keep in mind. Suppose we have chloride ion. Chloride is Cl minus. So for this we'll write chlorido. Chlorido. Cyanide, Cn minus, is cyano. Cyanide becomes cyano. Okay. Oxide. Oxide is O2 minus. It becomes oxo. Right. Imide. IMIDE. Imide is NH minus 2. It becomes imido. If you have azide, azide is N3 minus. It becomes azido. Okay. Nitride. Nitride is N3 minus. It becomes nitrido. Amide is NH2 minus, becomes amido. Carbonate. Carbonate is CO3 minus 2, becomes carbonato. Okay. Oxalate. Oxalate is C2O4 2 minus. It is oxalato. Okay. Like this. Chlorate. One more example. Chlorate. Chlorate is ClO3 minus, becomes chlorato. Like this we'll write. Ide becomes ido. Right? It becomes ato, like that. So you must keep this in mind. The naming, I know you can understand this easily, but this, anionic formula and the charge on this is very important, because we need to specify the oxidation state of metal also. Okay, so for that you should know the charge on the ligand. Okay, and then we can calculate. Okay, did you write this? Done? One more thing here you write down, that is nitrite. Nitrite is, see, nitrite is NO2 minus. And like I discussed last class, this is ambidentate ligand. So if I write O, NO minus, it means oxygen in the donor atom, and the name will be nitrito O. If it is NO2 minus, Then nitrogen is a donor atom and it is nitrito N. Got it? Can we move on to the next page? Let me know, please. Yeah. So this is one important thing, the naming of ligand. First point is this. Now, like negative charge ligand, how do we name that we discussed? If the ligand is neutral, then what we'll do? So that comes under second point, B. Okay. So neutral ligands are named same as their neutral molecules. Okay. For example, you see pyridine. Pyridine formula is this, and the name of this is pyridine itself. Okay. pH3. pH3 is phosphine. Okay. This is another example. This one is important. H2O, water. The name of this is aqua. The name of H2O is what? Aqua. CO is carbonyl. Okay. NO, nitrosyl. Urea, NH2CO, NH2. This is urea. Instead of O, if you write down S here, it is thiourea. Okay. It becomes thiourea. So these are the few examples of neutral ligand. One very important thing you must write it down. Like when you write down the name of the compounds, the spelling of the name is also important. Okay. So for that you write down in case of polydentate amino ligands, in case of polydentate amino ligands, we use single M in the spelling. Double M we won't write. Okay, that you must keep in mind. If you write down double M, your answer will be wrong. Okay, multiple choice, you can easily eliminate options if it is double M written over there. But while board exam, well, if the question comes in board exam, if you write down double M instead of single M, then you won't get any marks. For example, and this we only use when we have polydentate amino ligands. Okay, so polydentate means what? If the polydentate is the ligand whose denticity is greater or equal to 2. Okay, so except monodentate ligands, all other ligands are polydentate ligands. This is one thing. Next thing, we have polydentate amino ligands. Okay, for example, you see ethylene diamine. The structure is this CH2, CH2, and two amine group we have NH2 and NH2. Okay, So you see, this is the donor that we know already. And the name of this is what? Ethylene diamine. Diamine. But when we write down ethylene diamine, we'll write only single M here. We won't write AMMINE. Okay. If you write down AMM here, you will get laddu in the exam. Okay. So this is very important. Condition is what? Polydentate amino ligands. Amino ligands are the ligands in which the nitrogen atom, like this is amino ligands. Understood, Shreya? Got it? समझ में आ गई बात? Amino ligands are basically any derivative of amines. Nitrogen will be the donor in that case. Okay? Okay. So now, neutral and negative ligands we are done. The last one is positive ligands. Okay? So, third point in the naming of ligand, write down positive ligands, positive ligands ends with em suffix. We'll use em suffix. It is exactly similar to the negative ligands we have, where the suffix is ito, ido, ato, like that. But here we'll add em suffix into it. So for example, you see, if I take NH4 plus, okay, you see NH4 plus, if I write, the name of this will be ammonium. Okay, this is ammonium. If I write down NO2 plus, NO2 is nitro, so it is nitronium. Just will add em suffix into it. Okay, NO plus, NO is what? Nitrosyl. So NO plus is nitrocelium. Nitrocelium. Okay, one more you see, NH2, NH3 plus. So this is hydrazinium. Hydrazinium. Just will add em suffix into it. Okay, so this is what we did for the charged ligands. Okay, these are the rules we have. Next one, you see, copy it down first and let me know once you are done. We'll move on to the next page. Okay, so you see the next page. Point number D. All these are we use di, comma, tri, tetra, hexa, etc. We use di, tri, tetra, hexa, penta, tetra, penta, hexa, etc. If if the ligand is more than one, more than one, Okay, if the ligand is more than one. Okay. However, this point is important. However, if the if the name of the ligand includes a term like di, tri, tetra, etc., then if the name of the ligand includes a term like di, tri, tetra, etc., then we use we use bis, tris, tetrakis. We use bis, tris, tetrakis instead of or in place of di, tri, tetra, respectively. Okay. So, what is the meaning of this point that we'll discuss here? You see, suppose the ligand is this En2. This is what it is written. What is En ligand? Can you tell me? What is En ligand? Ethylene diamine. Symbol also you should know. En is ethylene diamine. Okay. Now you see the name of this ligands includes the term di here. The name of this is what? Ethylene diamine. Name of the ligands includes this di. Okay. And the 2 is already there, the whole twice of it. Okay. This includes di. So for this 2, we won't use di term over here because the name of this is what? It should be diethylene diamine. But since di is already there in the name of this ligand, so the name of this ligand will be for di or for 2, we won't use di but we use bis here, this one. For this, the name will be bis, open bracket, ethylene diamine. Okay. Why bis? Why not di here? Because di already present into this. Even if I write En3, then also we use tris ethylene diamine. Okay. Suppose if the example is this, then for this 3, because the name itself contains di term, so for this 3 we use tris here. So name of this will be tris, open bracket, ethylene diamine. Okay, this is again the example we have. But similarly, if you have this example, NH3 whole twice, this is what? Ammonia, right? Amine it is. 2 we have here, and the amine name does not include any terms like di, tri, tetra. So simply we'll write this as diamine. Did you understand this? Ethylene diamine, not amide. Shreya. Let me know if you understood this. All of you understood? Correct. Another point we have here, the next point in this, write down. If more than one ligand present, if more than one ligand present, then we'll write down the name in alphabetical sequence. Okay, in alphabetical sequence we'll write this. Okay, so this 5 points we have in the nomenclature of ligands. Now we see the next, which is the third point. Okay, these 5 points A, B, C, D, E we have in nomenclature of ligands. The third point is what? Oxidation state of the metal ion is shown in small bracket immediately after its name. A small bracket, generally parenthesis we use, okay, to write down the oxidation state of the metal. One last point we have in this, the complex positive ions and neutral coordination compound have no special ending, but complex negative ions end with 8 suffix 8 suffix. These are the rules we have. Copy it down and then we'll see some examples. We'll understand these rules. Copy it down first. Yeah. Now we'll see some examples here. Which is a very simple one we'll take. Suppose the molecule is this. The first one, K4 Fe CN6. K4FeCN6. Right? So now the first thing you need to find out the oxidation state of the metal. Okay, because that also you have to mention. Okay, so first step is to find out the oxidation state of the metal. Okay, so we know this is 4K plus. Can you tell me the oxidation state of iron here? Fe. What is the oxidation state? Two. Because this cyanide is -1 and potassium is +1. So this total charge here is what? +4. So this, the total charge on the complex will be -4. Did you understand this? -1 charge we have on one cyanide, so -6 this side. So the oxidation state of iron is +2. This is what I think we have. Now the name of this will be what? Cyano, and it is a negative ligands. Okay. So cyanide we can write what? Cyano. You see the rules I have given. For negative ligands, end with uh, O term will have in the last. So for Cn minus, we call it as cyano. Okay, you see here. For Cn minus, it is cyano. In some book, they also write it as cyanido. That is also you can write. It is the same thing. Cyano or cyanido, both are same thing. Okay. So Cn minus is cyano, and within the bracket, first of all, what we'll write? First we'll write the cation part and then the anion part. So since we have cation part positive here, this is simple. So we'll write simply potassium. Okay, K plus is potassium. And within the complex, we'll write first anion. So how many Cn minus we have? 6. So we'll write hexa. We'll have a gap between these two, cation and anion part. Potassium, hexa, cyano. Potassium, hexacyano, and iron we have, and the complex part is negative. So we'll write it as ferrate, and there is no gap here. Ferrate. When you write the name of the metal, just after this, you need to mention the oxidation state of the metal in Roman, like this. Potassium hexacyanoferrate. Got it? Understood this? The first thing, we'll write down the positive, the cation part first, and then the anion part. That's a simple thing. So cation is potassium, so potassium. Anion is the complex part. So within the complex part, we'll write down first this ligand and then metal. Correct? So ligand is Cn minus. So cyano, how many cyano? 6. So hexacyano. Ferrate, oxidation state is +2. 2, 3 important thing you have to understand. Hexacyanate iron I won't write here. I wrote here ferrate. And this is because of the rule number 4th. The last rule you see, what is given here? That if the complex positive ions and neutral compound we have, then there is no special ending. But if the complex ions are negative, then it ends with 8 suffix. Okay, that's why iron will write ferrate, because the complex ion is negative, so ferrate. Okay, we'll have a gap between the cation and anion part, right? Like here we'll have the gap. Apart from this, we won't have any gap between the metal and ligands. Must keep that in mind. These are small things, very important. And for nomenclature, these gaps also very important. Okay, if you put a gap here between this hexacyano and ferrate, it will be again wrong. And you will again get what? Laddu. Got it? What is the name of this molecule? Just you need to follow the rules. NiCN4, 2 minus. NiCN4, 2 minus. Tell me the name of this. Tell me the name. Tetracyno. Is it nitrate? See, first of all, it is an ion. It is not a molecule. It is not a complete coordination compound. It is the only negative part of that coordination compound. Yeah. It is the negative part of that complex. And again, since it is the complex part is negative, so when we write down the metal, so metal ion is nickel, so we should write nickelate because the complex part is negative and negative ends with 8 suffix. Okay, so we won't write nickel, but we write nickelate first of all. And within the complex, we'll write down the name of ligand first, which is 4 cyno molecule we have. So for 4, we'll write tetra cyno. Just a second, I'm coming. Sorry guys. So tetracyno, since the negative part we have, right? So the metal will write with suffix which is 8. Tetracyno nickelate. 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 And after this, we'll have the oxidation state of the nickel, which is +2. So we'll write like this. We always write oxidation state in Roman. Okay. So tetracyno nickelate. Got it? Okay. And one more thing, since it is an ion, it is not a complete molecule. So we'll write tetracyno nickelate, then oxidation state. Nickelate ion. Ion we have to write. Okay. Okay, nickelate ion. So you must keep that in mind. If the molecule is not given, ion we have given. So we always write down ion in the last. And there is no gap here. You see, again, the metal and ligand, there is no gap. Okay, and after that, immediate, like after the metal, we'll write down the oxidation number. Is it clear? Pizza is not good for health. Don't eat. Right? Another example you see. Third one. What is the name of this one? I'll write down the few molecules. You do it first and then we'll discuss. CONH3 whole 6 and Cl3. This one. Fourth one is COCl, NH3, 5, 2 plus. Again, it is a molecule, it is an ion. Fifth one, CONO2, 3, NH3, whole thrice, close bracket. This is also 3. Do these 3 first and then we'll see more examples. CONH3, 6, Cl3. What do we write here? First of all, tell me the oxidation state. Tell me the answer of this one. Always keep that in mind. We'll write first the cationic part and then anionic part. Cationic part can be anion, can be, cation. Sorry, the complex part can be cation, can be anion. And within the complex part, we'll write down the name of ligand first and then metal. Hexamine, cobalt 3 chloride. Is it right? Ardra is getting hexaamine, cobalt 3 chloride. You won't write any space between hexaamine and cobalt, likit. And 3 should be in Roman always. So, Ardra, your answer is correct. Spelling also you take care of. Amine you have written double M. Ardra, that is right. Because amine is here, it is a monodentate ligand, not polydentate ligand. Okay. So, name of this will be obviously the oxidation state. NH3 is 0. Chlorine is -1. So, here we have +3. Right? And this +3, since it is 0, so it is present onto this metal. So name of this compound will be, first we'll write down the cation, and cation here is the complex part, and within the complex part we'll write first ligand, which is hexaamine, amine, and then we'll write cobalt, no space here, cobalt. After this, the oxidation number, and then we'll give a space and we'll write chloride. Double M we won't write. No, double M we won't write. Hexamine. We'll have only single M here, not double M. Sorry. Got it? What is the name of this one? Again, you take care of, this is an anion. Sorry, this is an ion. Here is cation. Got it, guys? Tell me the next one. Pentaamine chlorocobalt 2 ion. Is it right? Adra, what is the answer? Tell me. Likhit is getting pentaamine chlorocobalt 2 ion. Chloridopentaamine cobalt 3 EM. We won't write EM here because the ligand is not positive. EMs are fixed. We only write if the ligand is positive. You see, you are mixing two things. EM suffix we use for ligand, not for complex. If the complex is positively charged, for that we have rule number 4. You just go through rule number 4. Hamsini, see rule number 4 and try it again. Shreya, what is the answer? Tell me question number 4. Ardha, done. Aditya, where is Paras today? Why chloride, Shreya? Cl is a negative charge. See, I tell you one thing. अपना दिमाग नहीं लगाना है. Don't put your brain here. We have rules. Follow that rules. That is it. Got it. You don't have to put your brain into this because it is nomenclature. Nomenclature for organic compounds you must have done. There also we are following the rules. So here also we'll follow the rules and write down the name. Right? Another thing, the ligand is amine. It's not, the ligand name is amine. It is not pentaamine. You understand this point? The ligand is NH3. It is not 5NH3 is the ligand. 5 is the number of ligand that is present. So when we write down this in alphabetical sequence, then we always take the name, the first letter of the name of the ligand. We won't consider di, tri, tetra and all in this case. Paras went for family function. What kind of family function? Your marriage, Likith. Huh? Acha, tell me, did you understand this? Two things. First, what you have to understand here, you see the complex part is positive. Rule number 4. We use rule number 4, correct? So rule number 4 is what? There is no special ending of neutral or positive charged complex, correct? So we won't have any special ending over here. And there is more than one ligand present. So we'll write down the name of ligand in alphabetical sequence. Correct? So one ligand is amine, other one is chloride ion. So we won't consider pentamine, P over here, but we consider the name of the ligand, which is amine. So A and C. So first we'll write down the name of the ligand, which is pentamine. Pentamine, neutral ligand, no special ending. Correct? Pentamine. Then we have Cl minus. So for Cl minus, we'll write chlorido, no space here, chlorido, and then the metal, which is cobalt, no space again, cobalt. Oxidation state of cobalt is what? This is 0. This is -1. We'll go this side. +3. +3 will be here on this cobalt. So cobalt 3. And after this, iron. Without any space. Got it? Ritu, you there? Did you understand this? Rashmi, what about you? Let me know if you have any doubt. Why chlorido? Likhit, you see, chlorido is because Cl minus. Cl minus is chloride ion. So negative charge ligand end with ido suffix if it is chloride. So chloride becomes chlorido. That's why. Why not chloro? Chloro also we use, chlorido also we use. Like cyano we use, cyno, cyanido, cyanido. Similarly, chloro, chlorido also you can use. Generally we use chlorido. Got it, all of you? So must take care of this thing. This penta term we are not considering in uh, alphabetical sequence. Write it down there. Not considering in alphabetical sequence. Understood? Important this one. Now this one you see, NO2 is what? NO2 is nitrite ion, and this is again amine. So nitrite. So name of this will be what? Nitrito, it becomes nitrito. Amine will be amine only because it's negative charge ligand. This is neutral ligand. What is the name of this? Tell me. Triamine, tri. It is nitrato. Hamsini, how it is nitrato? What is NO2? That's why you see, if you do not remember the name of the ligand, you won't get it right. Okay? NO2 is nitrite. Just now I have given, go through it. NO2 is nitrite, so it becomes nitrito, not nitrato. ट्राइनाइट्रो अमाइन अरे लिखित कुछ भी लिख दे रहे हो हाउ इट इज ट्राइनाइट्रो अमाइन अरे अपने मन से नहीं करना है भाई रूल्स है रूल्स को अप्लाई करना है दिल से नहीं करना है दिमाग से करना है डिड यू अंडरस्टैंड दिस लिखित लिखित while studying follow your brain not heart Got it? So it is amine and it is nitrito. So first of all, we'll write amine alphabetical. So this will be triamine. Okay, triamine, and double M will be there. Take care of this. Triamine, then without any space, trinitrito, because it is nitrite ion negative charge I2 suffix will be there. Triamine, trinitrito, cobalt. What is the oxidation state of cobalt here? It is -1, so -3, -3, so +3 will be the oxidation state of this. So 3 will write here. Got it, all of you? Yeah, right. Understood, all of you? Let me know. NO2 is a negative charge ligand, Shreya. NO2 minus. See, either oxygen or nitrogen is a donor atom. So NO2 is a negative charge ligand. Nitronium is NO2 plus. It is not positive charge. NO2 plus will be written over there. NO2 plus is not written, no. There's no positive charge over there. It means it is a negative charge ligand. Nitrite ion. Got it? So see, these examples are very important. This gives you the whole idea actually. When you have more than one ligand, then this di, tri, tetra, hexa, penta, whatever term we have, this term we won't consider in alphabetical sequence. Okay. Here also all these negative charge ligand end with O suffix, right? Another few more examples we'll see which are important. Like for this one you do CONH3, CONH3, and we have 4 H2O Cl, bracket close, and outside the bracket we have one chlorine present. What is the name of this one? What is the name of this one? First of all, you try to get the name of ligand, and then according to the alphabetical sequence, you arrange them. Complex part is cation here. So we'll write down first cation and then anion. Tetraamine, then aqua, chlorido, cobalt, 2 chloride, right? But then again, cobalt 2, and then we'll have a space and then chloride. Understood? Cobalt 2 will always write give a space between cation and anion, whether it is complex or no or whatever. The cation is complex or non-complex. We always put a space over there, right? So the name of this is everything is right for both of you, Hamsini and Shreya. The only thing will have a space between this cation and anion part. So name of this will be, this is amine first. So tetraamine. For H2O, it is aqua, chlorido, then metal, which is cobalt. Oxidation state of metal is -1 here, and here -1. So we'll have 2, and then space chloride. Yeah. What about this one? One or two more examples we'll see. CuEN2SO4. Tell me the name of this. See, these nomenclature questions in the competitive exam, if you can find out the oxidation state of the metal, with that only you can eliminate two options easily. Like most of the time, you can do that. How it is cuprium, Shreya? What rule you followed to write down this cuprium? Is there any rule I have given you for metals? EM suffix we write for ligands, right? Not for metals. Did I give you any example in which we have taken EM suffix for metal? Hamsini, Shreya, both tell me. What rule I have given you, it is mainly for ligand. You see that? EM suffix we'll use when the ligand is positively charged. Got it? Paras, what is the answer? Bis, ethylene diamine, copper. Is it 4 or 2? Ardra, it is 4 or 2. Ian, what is the charge on ethylene diamine? Tell me, Likhit and Adra. What is the charge on ethylene diamine? Ian. Tamikta, tell me the charge. Ritu, tell me the charge on ethylene diamine. Yeah, En is neutral, guys. It's not negatively charged. That's why I told you in the beginning only. You should know the charge on the ligand. Otherwise, you'll make mistake in calculating oxidation state of the metal. Correct? So En is neutral and sulfate is -2. Correct? So this is -2. So total on this complex will have +2 charge. And since it is neutral, this +2 charge will be on metal. So oxidation state is +2. Right? If you know this, it is +2, then you can eliminate one or two options easily. Okay, so must you keep this in mind that what is the charge on different ligands. Now coming back to the nomenclature of this, first we'll write down cation part and then anion, right? So cation part is this, and En is the polydentate ligand. Okay, polydentate amino ligands. So we'll write down for 2, we'll write down bis open bracket. You can write down ethylene diamine, or you can also write down ethane 1,2 diamine. In fact, this is better way to write because we know the position of amine, whether it is present on the same carbon or two different carbon. So if you write down this way, it will be better. Bethane, bis ethane 1,2 diamine, and then we'll write what copper. Oxidation state on copper is 2, and then some space sulfate. Understood, all of you? Okay. Now these are the examples you will see in the book. I'll send you some more examples on this so that you can go through. We'll see some different types of example now. Okay. So I'll go to the another page. See what we'll do when both cation and anion part are complex. Okay, just one or two examples. This is not that important, but we'll see one example here. So what we'll do when we have complex cation and complex anion part. Both cation and anion are complex here. Then what we'll do? Okay. So you see one example I'll write down. Everything is same here, but the only difference we'll have here to find out the oxidation number of each metal. Okay. And for that, what we'll do, I'll just tell you with this example. Here we have copper CN6. Okay, how to find out the oxidation number of metal here? So for what we do, will find the total charge on ligand and will divide it into two equally. Okay, so see, this ligand is neutral and this is -1. Total charge is what? -6. So -6 will divide equally over here metal, so it is +3 and +3. This is how we'll find out the charge oxidation state of the metal, right? And hence the name of this ligand will be what? 6-amine. This is the complex cation part, complex anion part. So we'll write down this first and then we'll write down this. It is exactly same. So it is hexamine, right? Chromium, chromium 3. Then we'll have some space. Hexacyano, cobalt 3. This is what the name. Got it? Done. बोलो भाई समझ गए? Okay. Do this one. There's one example I'll give you here. PTNH3 4 bracket close, and then we have CuCl4. This one. What is the name of this? Tetraamine platinum 2, correct? Tetraamine platinum 2, tetrachlorido copper 2. Right, Shreya. Correct. Look it again, how it is cuprate. See, how can you be so partial here? Copper becomes cuprate and platinum is platinum only. Then according to this, you should write platinumate. No, look it. It should be platinumate. No. Yeah, it's copper, not cuprate. Hexachlorido, correct. Now, okay, so you understood this. Now, one just last example we'll see. The name of this one, first of all, I'll write down here. So it is hexamine. This is what. Okay. One last example you see. And this is for bridging group group in bidentate ligand. One just last type we'll see. This one is least important. They won't ask generally questions onto this, but since it is there, we'll just go through one example. Okay. So it is like, for example, one example, if I write down, suppose if the molecule is this, and for this molecule, you need to write down the name. En2, cobalt, and here we have OH, OH. This is bridging ligand. Okay, these two ligands act as a bridge between these two metals. En2, and then we'll have SO4. This is the molecule we have, bridging group ligands. Okay, now in this also, first of all, the first thing is to find out the oxidation state of the metal. So again, what we'll do, we'll just find out the total charge. Like you see, this is 0, this is 0. OH, we know it is -1, it is -1. Sulfate ion -2. So here we'll have +4 on this whole entire the complex part we have. We'll have +4 charge because SO4 whole twice we have. Okay. So now this 4 plus 2 becomes 6. And this 6, because this one and this one goes this side, this 6 will equally distribute over the metal atom, which is cobalt here. So this oxidation state of cobalt becomes +3, and this is also +3. Total charge divided by 2. 4 plus on this. This -1 goes this side, -1 goes this side, so +6 will have total. Okay, okay. So the name of this will be what? It is ethane 1, 2 diamine. 2 will have here. So two ways you can do this nomenclature. The first one we are discussing first. We'll write on bis open bracket ethane 1, 2 diamine bracket close. And then we have what? Then we after this we have a metal, that is cobalt without any gap. Oxidation state of cobalt is 3, again without any gap. Okay, and it is attached with hydroxy. So whatever the bridge ligand we have, to mention the ligand which is connected as a bridge, we'll use a term here, and that term is mu. Okay, so mu hydroxo, because OH negative, so hydroxide becomes hydroxo. Mu hydroxo, and we have two hydroxy group here. So again mu hydroxo. After this, we'll write down this ligand first. Bis ethane 1, 2 diamine 1, 2 diamine bracket close, then metal cobalt oxidation state 3, and in the last we'll have some space and then sulfate. Where is tetramine? Or in the last page, is it? Yeah, it's tetramine, not hexa. I'm sorry. Correct it. It is so it is tetramine platinum tetrachloride. Correct. Okay, so we'll start from this side. We'll write down the name of this bis ethane 1, 2 diamine, and then metal, oxidation state, mu hydroxo, mu hydroxo. When you see this term, mu that is attached here, it means this ligand, whatever this ligand is attached as as a bridge between the two metal. That's what it means. So bridging group ligand will always write with a term that is mu that we use for that. Got it? Bridging group ligand will use a term mu for this. Yes or no? Okay, can we move on? Tell me. Okay. See, this is one way to write down the nomenclature of this compound, or we can also write down the same molecule in different manner. How many total ligands we have? This E and this is 2 plus 2, 4. So we'll write this to write down separate. Instead, what we can do, these two terms will write down together, and it becomes tetrakis ethane 1,2 diamine, single M. Okay, then di mu hydroxo, metal is same. So again we'll write cobalt 3, then sulfate. Right? Again, one more thing you take care here. We won't write here dicobalt. Dicobalt we won't write. We write only the name of the metal, that is cobalt. This means there is a bridge between the two metal atom we have here. That is cobalt only. That is also, this way also we write. Basically we club these two simply. This is not that important. So just one example I have done for this. Okay. Right. So these are the few examples we have discussed for the nomenclature of coordination compound. Nomenclature also based question they also ask in the exam. So again, this one is important. Charge on ligand you must know. Now, the next part again we are going to discuss the bonding in coordination compound. The bonding in coordination compound, again, like I said, there are different bonding theory we have for this. Like if you remember in chemical bonding, we have again valence bond theory, molecular orbital theory, Lewis dot structure, and all. There are many things we have. So similarly, here we have also the different bonding theories. Okay, because different molecules shows different kinds of bonding. So one theory is not true for all kind of coordination compound. So that's why we have different theories here. So the first coordination compound or first theory which is given for the bonding in coordination compound, we call it as Werner's coordination theory. Okay, and the heading you write down here, Werner's Werner's coordination theory. Okay, now first of all we need to understand what is the main postulates of this theory are. Okay, so the main postulates of Werner coordination theory, write down. According to this theory, the first point that is given here is a metal has, or every metal has two types of valency. Two types of valency. Okay, what are the two types of valency? The first one, A in this, is primary valency. And the second one is secondary valency. Okay, so we'll see first what is primary valency we have. Okay, so write down into this primary valency, and it is important. It corresponds to the oxidation number of the metal. Oxidation state of the metal. Means first thing is what? If you need to find out the primary valency of the metal in a coordination compound, we'll find out the oxidation state. If it is 2, then primary valency is 2. If it is 3, primary valency is 3. Okay? Second point, this is non-directional. What is non-directional? We'll discuss this in the last, like when we discuss this secondary valency also. We'll take an example and then we'll discuss. Okay? It is non-directional in nature. And the third nature of this kind of bond, that its attachment with metal with metal is shown by dotted line like this. One very last point, and the important also, the primary valency, it is, I'll write down, it is neutralized or satisfied by neutralized or satisfied by the negative ions. Okay, negative ions, such as if you have Cl minus present in the molecule, SO4 2 minus presence, all these negative ions satisfies the primary valency of the metal. Okay, I know you must have some doubt in this. What is this non-directional, neutralized, satisfies, and all? So I'll discuss all these things. What you have to keep in mind, like so far, that if you need to find out the primary valency, find out oxidation state. First thing. Satisfies means what? Suppose if I take one example, and in that example, we suppose we have NH3 or Cl also present. So NH3 is a neutral molecule. So that NH3 molecule is not responsible for the primary valency of the metal. Only chloride ion is responsible. That's what the meaning of this we have. It is neutralized and satisfied by the negative ions. Got it? When we take one example, you will understand this. Okay, so first of all, you write down this thing, and then we'll take one example, and then again we'll discuss. So, like primary valency, we have discussed. Similarly, we have the second type of valency, and we call it as secondary valency. Okay, secondary valency. Like primary valency represents the oxidation state of the metal. Similarly, secondary valency represents the coordination number of the metal ion. Okay, so this is associated with the coordination number. Coordination number of the metal. Very important point is this. This one is non-directional. This one is directional. And since we have direction, so it is responsible for stereoisomerism. Stereoisomerism of the complex. Okay, this is one thing. Again, this part we'll discuss in isomerism of this coordination compound. Like here we have attachment in this dotted line, but here we have attachment like this solid line we have here. Attachment between metal and ligand is represented by solid line. Okay. One last point in this write down. It is satisfied by either negative ion. It is satisfied by either negative ion or neutral molecule, both responsible for the secondary valency. Neutral molecule or negative ion. Okay, so if NH3 and Cl3 is present, then both responsible for the primary valency. Sorry, secondary valency. Okay. Can we move on to the next page? All of you have written, tell me. I'll just explain this with an example. First of all, you tell me, did you copy this? Okay. Now you see this. This is also important. Okay, they ask question over here. Now suppose if I write down one example, and the molecule is CONH3 cobalt NH3 6 and Cl3. This is the molecule we have. Can you tell me what is primary valency for this molecule, PV, and what is secondary valency? First of all, you tell me this, because you know to find out the oxidation state, you know to find out the coordination number of the metal. So first you tell me what is the primary valency and what is the secondary valency. Primary valency 3. And what is the secondary valency? Secondary valency 6. Correct. So first of all, you already know to find out the primary valency and secondary valency. Primary valency is nothing but the oxidation state, which is +3. So primary valency is 3. Secondary valency is nothing but the coordination number, which is 6, because we have 6 monodentate ligand in this. Okay. Now, you see, if I draw the structure of this, right? So a structure of this will be something like this. If I can draw the structure here, we have metal in the center, and around this metal we have 6 NH3 ligand, right? So which is nothing but like this. One NH3, suppose like this. Another one is this. Another one is this. 4. And then 5, 6. Okay. यहाँ तो नहीं ना आपसे नहीं आपको यहाँ हम जगह है वो यहाँ से जाएगा Okay, so this is NH3. This is NH3. This is NH3, and this is NH3, right? And we have 3 chlorine atom attached with it, which is nothing but this. This is chlorine atom. See, this is the +3 oxidation state we have, which is nothing but the primary valency. It is because of the 3 chlorine atom, because the oxidation state of metal is because of this chlorine only. Correct? Because NH3 is neutral. So this is only responsible for the primary valency of the metal. Right? So generally what we say, and the second thing, if you see, if I go to the last page that we just now did, you see what I have written over here. It is neutralized and satisfied by negative ions. Okay? It is satisfied by either negative or neutral molecule. So any neutral molecule cannot be responsible for the primary valency of the metal. First thing is this. What I said, it is neutralized means satisfied by, both are same term actually here. You can use it is satisfied by this or neutralized by this. Neutralize means what? The primary valency of the metal is possible because of the negative ion. That's what the meaning we have here, right? So thing you have to keep in mind that any neutral molecule or ligand which is present in the complex can never be responsible for the primary valency of the metal. This is what it means. Okay, but for secondary valency we can have negative ion also or neutral molecule also, both possibilities. Now I'm again going to this next page. Since all these chlorine atom is negative charged, so all these are responsible for the primary valency. Okay, and since this chlorine atom is present outside this the complex bracket, so when you dissolve this can go into the solution as Cl minus, means ionization of this is possible. That's why primary valency we also call it as ionizable valency. Ionizable valency, both are same term actually. Mostly we use primary valency and secondary valency, but since it can ionize, hence ionizable valency. Similarly, secondary valency, this won't ionize because it is present in within the square bracket, the complex part. So this we call it as non-ionizable valency. Is it clear? Is it clear, guys? Tell me. Yes or no? Write down CLR if you understood. Quick. All of you, quick. See what I said, that primary valency is because of oxidation state, right? And negative ion satisfies primary valency. Suppose if this molecule we have, so in this NH3 is neutral, Cl is negatively charged. So primary valency of this metal cobalt is satisfied by only Cl minus because it is the negative ion. This is neutral ion, right? That's why the primary valency is 2, and chloride ion satisfies the primary valency of the metal, which is cobalt here. That's what it means. And that is why this chlorine atom is attached with a dotted line here. Because we know the primary valency is, the metal which is the ligand which shows primary valency is attached with a bond which we represent by this dotted line, not by the solid line. That's what it means, right? So if I write down here, secondary valency is satisfied by 6 NH3 molecule, and primary valency is satisfied by 3 chloride ion, negative ion, right? No doubt. Now, in this, another example we'll see. Suppose if I write the molecule like this, CONH3, NH3, 5, 1 chlorine inside, and the 2 chlorine atom present outside, like this. CONH3, 5, Cl, Cl2. Okay. Now you see, generally what happens for any metal, the coordination number is fixed if the ligand is same. Coordination number won't change. Okay. For any metal, the coordination number won't change. First of all, if I ask you about the primary valency of this compound, right? The primary valency, oh, I'm sorry. If I ask you the primary valency of this compound, PV, that will be the oxidation state of the metal, which is nothing but -1 here, right? So +2 on this, and chlorine is -1. This is 0, so that is 3 plus 3. Primary valency is +3. What is secondary valency? Again, like I said, for a given metal, if the ligands are same, right? This is the thing we have, ligands are same here. So a secondary valency like this compound, it is again nothing but the coordination number, which is 6. And you can find out this also. 5 nitrogen and 1 chlorine, coordination number is 6. Fine. Coordination number is 6. Now, if you draw the structure of this, which is this one, 1, 2, 3, 4, 5, and 6. Okay. So the coordination number is this. The dot, the solid wedge, is nothing but the secondary valency. So I'll write down here the ligand which satisfies the coordination number, the secondary valency of this, which is 5 NH3 molecules. You see NH3 here. Oh, it is cobalt. NH3 here, right? Again, it is NH3 because we know neutral molecules. And we also know the secondary valency is satisfied by the neutral molecule and negative ions. Correct? So we have 5 neutral molecule and 1 negative ion. Secondary valency is 6. So yes, this 5 will satisfy the secondary valency, and the sixth ligand is nothing but chlorine here. Okay, we have 2 chlorine atom outside which satisfies the secondary primary valency of this metal, that we can draw the structure like this. This is chlorine and this is the another chlorine atom, right? So the chlorine atom which is present outside here from the complex, that I have written like this because this is ionizable, right? This is ionizable. This chlorine is not ionizable, right? This is ionizable valency. But like I said, this negative ion satisfies both primary and secondary valency. You see the previous page, I'll show you. This one you see. The negative ion, here also we have negative ion, satisfies primary valency, and negative ion satisfies secondary valency. To sum up this, what we can say, that negative ion satisfied both kind of valency, whether it is primary or secondary. This chlorine atom, which is present inside this complex, coordination like the complex, this chlorine satisfies primary valency as well as it satisfies secondary valency also. The structure of this will be this chlorine with a solid line and a dashed line like this. This is what it means. Negative ion satisfies both primary as well as secondary valency. Is it clear? So the structure of this will be this one. So if I write down here, the secondary valency is satisfied by 5 NH3 molecule and 1 Cl minus ion. And primary valency is satisfied by 3 Cl minus ion. NH3 cannot satisfy the primary valency because it is neutral. Clear? Yes. Yeah, just 2 minutes, Hamsini, 2 minutes. Let me finish this, I'll give the break. All of you understood? Correct. Now you see that another example, two more example I'll see. The third one is this similar molecule CONH3. I'll write down 4 here, Cl2, and then the chlorine outside. This is the third one. And fourth one is this CONH3 whole thrice Cl3. This one. So I'll draw the structure for this one. So structure will be, we have cobalt, right? So 1, 2, 3, 4, 5, and 6, right? And one chlorine atom outside, so which is attached with the dotted line like this, primary valency. And here we have 4 NH3. So 1, 2, 3, and 4. And this we have 2 chlorine, because 4 satisfies here also. You see the coordination number I did not write here. The primary valency is nothing but what? Oxidation state of the metal, which is 3, and secondary valency is nothing but 6. Okay, so out of this 4 NH3 satisfies secondary valency, and 2 chlorine atom satisfies secondary valency. So this is satisfies by 4 NH3 molecule and 2 chloride ion. But say primary valency, like I said, it is only satisfies by 3 Cl minus ion, negative ions. So the exact structure of this will be, out of 3, this 2 chlorine atom is attached with the dotted bond, also primary valency. Clear? Similarly, the structure of this I'll draw here, which is a CO 1, 2, 3, 4, 5, 6. Okay, so NH3, NH3, and I have written it randomly. There is no pattern. Okay, right now there is no pattern, so I have just written it randomly. Okay, so don't think about it. What is the bond angle and all? So since we have 3 chlorine inside, again you see the primary valency is 3, secondary valency is 6. All these 3 negative or chloride ion satisfies both primary and secondary valency. This is the structure we have. Understood? Yes, CLR, quickly. CLR guys. Okay. Now, one question that they ask here about molar conductivity of these this kind of molecule. They ask about the order of molar conductivity. Molar conductivity, we have already discussed it in electrochemistry, and we know as the number of ions increases in the solution, molar conductivity increases. So if you put this molecule into the solution, we'll get 0 ions, right? Because all like these atoms are present within the complex. And here we get 1 Cl minus and 1 this complex ion. So we'll get 2 ions here, right? Previous one you see, previous one, here we'll get 3 plus 1, we'll get 4 ions here, and here we'll get 2 plus 1, 3 ions, right? So as the number of atom increases, or the number of ions increases outside the complex part, the conductivity or the molar conductivity of the complex increases. So molar conductivity, if order I'll write down here, it will be maximum for 1, then we'll have 2, and then we'll have 3, and then we'll have 4. So basically, the number of ions that you are getting, total ions, when you put these complex into water, that gives you the order of molar conductivity. More number of ions, more molar conductivity. Understood? And the last thing we are discussing here, in this only, the last one more property we'll see. Like I said here, this secondary valencies are directional in nature. Okay, directional means what? The bond angle of this bond will be fixed. It won't change. This bond fixed. It won't change. This bond angle won't change. So basically, in other words, if I say the position of all those atoms or molecules which satisfies the secondary valency of the compound is fixed with respect to the metal atom. Solvation dependent upon size. We are not talking about solvation share here. We are just talking about the molar conductivity of the solution. That depends upon the number of ions, because we have similar kind of ion present in the four compounds. The only difference is what? We have complex and Cl minus, complex and Cl minus, complex and Cl minus. But the only difference we have here is the number of ions present in the solution depending upon what molecule we are taking, 1, 2, 3, or 4. Right? So basically, more number of ions in the solution, more will be the molar conductivity. That's what we are discussing. We are not talking about the solvation energy. Yeah, solvation will be difficult if the size is large, size is big. That is true for all the molecules. Yes. Yeah. It was only among these 1, 2, 3, and 4. Correct. Now the thing is, I'm talking about the directional properties. Like I said, secondary valency is directional in nature. So all the atoms or groups which satisfy secondary valency, their bond angle and the position with respect to metal will be fixed in the space, in the three-dimensional space. And that is why these molecules shows stereoisomerism. Okay, so that is stereoisomerism we'll discuss in the last of this chapter, geometrical and optical isomerism of coordination compound. Got it? Why it shows coordination stereoisomerism? Because the atoms or molecules which show secondary valency, their position is fixed. They are directional in nature. This Cl, if you remove from this and attach here, it won't make any difference. You remove from this, attach here, it won't make any difference. But NH3 position is fixed. All the atoms or groups that shows secondary valency, their position we cannot change. It is fixed with respect to the metal. Got it, all of you? Yes, guys, all of you, CLR, quickly. Cool. So we'll take a break now. We'll resume the class at 8:30. Half an hour class we'll have. 8:30 we'll resume the class. Take a break. Okay, guys, are you there? Can you start? Just a second. Okay, so see, like I say, this is the first attempt towards the bonding of coordination compound to understand the bonding in coordination compound. But like I said, there are different theories we have in the bonding of coordination compound. This was the first attempt, and obviously we have some drawbacks in this theory. Okay, so what are the drawbacks we have for coordination compound in Werner coordination theory? That we'll see first. Okay, so next write down drawbacks of, okay, drawback of Werner coordination theory. Okay, the first drawback: why only few elements, few metals, only few metals, only few metals, only few metals consist of properties of coordination compound. The reason behind this, or simply write down why, this question was not explained by the Werner coordination theory. Why only few elements shows the properties of coordination compound? This was not again explained. Like, the properties, like magnetic properties. What is the magnetic property of coordination compound? Magnetic and optical properties, optical properties was again not explained by the Werner's coordination theory. And why the bonds has, it is actually the same thing in optical properties. Why the bonds has directional properties? Bond has directional properties. This is also not explained by Werner coordination theory. These are the few drawbacks we have in the Werner coordination theory. Now, to understand all these things, we have a new theory of coordination compound, and that we call it as valence bond theory. Okay, so the next theory of coordination compound we have to understand here is valence bond theory. Okay, so I'll write down the next theory. This one is again important. Valence bond theory. It is similar to the theory that we have already done in coordination, sorry, this chemical bonding. In short, we write it as VBT, valence bond theory. Okay, like Werner coordination theory. Here also we have the few postulates of this theory. Okay, the first, write down the main postulates. The main postulates of this theory are: the first point, the central metal atom, the central metal atom loses a required number of electrons, a required number of electrons to form iron, and this number of electron, we call it as the valency of the metal. Okay, the number of electron loses is nothing but the valency of the metal. Second point, depending upon the coordination number, depending upon the coordination number, the central metal atom, the CMA, has equal number of vacant sp and d orbitals, and these orbital collectively forms hybrid orbital. Okay, third one, in case of strong ligand, this one is important. Okay, this is the new point we have over here. This we already did in chemical bonding last year. You must have done it. This third one is important. In case of strong ligand, in case of strong ligand, there may be some rearrangement there may be some rearrangement against there is a rearrangement against there may be some rearrangement against the Hund's rule. Okay, this one is important. Fourth point, you see, the ligand attached to the ligand attached to the central metal atom with coordinate bond and possess a considerable amount of polarity. Means the bond is polar. Okay. And the last thing is, if the complex contains unpaired electron, I'll just write down in short, unpaired electron, then the complex is paramagnetic. If there is no unpaired electron, all electrons are paired, no unpaired electron, it is diamagnetic. If the complex contains unpaired electron, paramagnetic, otherwise diamagnetic. Write it down. Done? Did you copy it? Tell me. Okay. See, these are the postulates of valence bond theory. All these points are same. We have only difference here. This third point you keep in mind in case of strong ligand, and this unpaired paramagnetic, and there's no unpaired electron, diamagnetic. Okay. See, like we till now we do not have any information regarding whether the electron is strong or weak. Okay. So this property of electron, whether it is strong or weak, that we'll understand in the next topic, which is crystal field theory. Okay, crystal field splitting we'll see over there, and there we'll understand which one is strong ligand and which one is weak ligand. In general, I'll tell you one thing: if all halide ion donor, okay, X minus, are the weak ligand, okay, oxygen donor is also weak ligand. In general, nitrogen and carbon donor atom, if it is present, okay, nitrogen and carbon donor atom, if it is present in the ligand, then it is considered to be the strong ligand. Okay, if the ligand has nitrogen and carbon atom as the donor atom, then it is a strong ligand. Okay, this you have to memorize. In general, it is okay. It's not always true. Okay, but with this data, you can do most of the questions basically. Correct. So for this thing, like I said, what is a strong and what is weak ligand? We'll discuss that in crystal field theory. Okay. But here we'll discuss some questions based on VBT, valence bond theory. But I'll give you the information of which ligand is strong, which ligand is weak. Okay. Now you see the first type we are considering here is the case one we have for coordination number 4. For all those complexes whose coordination number is 4, we'll try to find out the hybridization and geometry of these kind of complexes. This thing, I'll just draw a table over here. And just a second. Draw this table. See, here we have the first one is coordination number, geometry, and then hybridization. Coordination number can be 2, 3, 4, 5, and 6 possible. Okay. If coordination number is 2, the geometry will be linear. This you have to memorize. Hybridization is SP. Coordination number is 3. Geometry will be trigonal planar. Hybridization is SP2. Coordination number is 4. It can be either tetrahedral or square planar. Tetrahedral geometry, hybridization is SP3. Square planar, hybridization is DSP2. If it is 5, then it is trigonal bipyramidal. TBP is trigonal bipyramidal. Okay, or we can also have square pyramidal. Hybridization can be anything DSP3 or SP3D. Any, like, it is not like TBP has this, square pyramidal has this. It depends upon the properties of the molecules. We'll discuss that. Okay, but if geometry is square planar, hybridization is always DSP2. Tetrahedral, it is SP3. Okay, these two is specific. These two are not specific here. Similarly, 6, we have either we have octahedral or we have a square bipyramidal. Square bipyramidal or octahedral. It is D2SP3 or SP3D2. Anything possible here. Okay, this is the coordination number with geometry and hybridization. Okay, the most important part in this chapter we have for coordination number 6. Okay, coordination number 6. Now you see, one or two questions we'll discuss for coordination number 4. And the question is, for the molecule is, suppose we have NiCl4 2 minus. This is the molecule we have. We need to find out in this the hybridization of this molecule. We need to find out geometry. We need to find out magnetic property, number of unpaired electron. All these things we need to find out. Okay. Now, the first thing you should know to solve this kind of question, very important question we'll have. This kind of questions are very important for the exam point of view. The first thing you should know to do this kind of question is the nature of ligand. Okay, the nature of ligand. And the nature of ligand, when I say, it means whether the ligand is weak or strong. This you should know. Whether the ligand is weak or strong. If the ligand is weak, you see what we have the postulates here. In case of weak ligand, you see the point number 3rd, which is the most important point we have here. In case of weak ligand, strong ligand, there may be some rearrangement against the Hund's rule. Okay, so this thing also we'll discuss, and it is only possible in case of strong ligand. If the ligand is weak, this rearrangement will not consider. Then according to Hund's rule, the electron will fill into the orbital. Correct? That also we'll see. But here, like I said, halide ions are the weak ligands. Okay. So what we can say, Cl minus is the ligand here, and it is a weak ligand. This is the first thing you should know to solve this kind of question. Now the second thing is what? The oxidation state of the metal. The oxidation state of Ni is what? Can you tell me the oxidation state of Ni? What is the oxidation state? Two, right? Oxidation state is +2. Okay. So you see, so oxidation state is 2. Next, what we have to do here, we need to write down the electronic configuration of Ni2 plus. Okay. We need to write down the electronic configuration of Ni2 plus. So for this, first of all, we'll write down the electronic configuration of nickel, which has 28 electrons atomic number. So it will be argon 18, 4s2, 3d 8. Okay. Ni2 plus will have, so 2 electron will have to take out, and which is coming out from the outermost orbital, which is 4s orbital, right? So argon 4s0 and 3d 8. This is how the configuration we have. Okay. Now you see, if I draw the orbital diagram of it, first of all, we'll have 3d, 1, 2, 3, 4. It is 3d. Then we have 4s. Then we have 4p. Correct? This is 3d orbital. This is 4s. And this is 4p. Now, first of all, you see, this molecule, we have 4 chlorine ion, right? And each of these Cl minus donates electron to the metal. Okay, so if I draw this in the next page, you see, nickel is present here at the center. And around this nickel, we have 4 Cl minus ion, which is donating electron and trying to make bond with this nickel like this. Okay. So each of this chlorine donates electron, correct? One pair of electron, each chlorine donates. So the number of orbital this nickel requires to accept this pair of electron is 4. Because total 4 chlorine atom we have, each chlorine atom donates one pair of electron. To accept this, we required 4 vacant orbital. 1, 2, 3, 4. Because if the orbital contains one electron, ligands donates a pair of electron. The orbital which has only one electron cannot accept the 2 electron which is coming from the ligand. Correct? So we require, according to the coordination number, will require equal number of vacant orbital which can accept those electrons which is coming from the ligand. Right? So in this question, we require 4 vacant orbital. Here you see, in this question, will require 4 vacant orbital since the coordination number is 4. If it is 6, then we'll require 6 valence vacant orbital. Now you see the next thing here. This 4s has 0 electron, 3d has 8 electrons. Correct? And how do we fill the electron? According to Hund's rule, 1, 2, 3, 4, 5, 6, 7, 8. This is Hund's rule. If the ligand is strong here, then this distribution won't follow Hund's rule. That's what the meaning of that third point. In case of strong ligand, there may be some rearrangement against the Hund's rule. That's what the meaning. But that we'll discuss also when the ligand is strong. So we'll focus on this question right now. 3D8 configuration is this, 4s and 4p. So what happens, since we requires 4 vacant orbital, these 4 orbital goes into hybridization and forms 4 vacant hybrid orbital, 1, 2, 3, and 4. Correct? 1s and 3p combines to forms this 4 vacant orbital. So it hybridization will be sp3. 4 vacant orbital, each of these orbital accepts a pair of electron from the ligand and forms the bond. Right? So hybridization is sp3. The first part we are done here. And we can say the hybridization of this molecule is sp3. Right? Since the molecule has 2 unpaired electron, you see here, the molecule has this unpaired electron will be as it is. The molecule has 2 unpaired electron. Hence, if it is unpaired electron, magnetic property is what? It is paramagnetic. Okay. So the other two questions we have here, the number of unpaired electron, number of unpaired electron is 2. Hence, it is paramagnetic. If there is no unpaired electron, diamagnetic. And if the hybridization is sp3, geometry is what? Geometry is tetrahedral. That is how we'll solve these kind of questions. How many of you understood this? Any doubt, let me know, please. All of you, let me know. No doubt, right? So write down to this Cl minus, one point to write down. Halide ion or Cl minus is a weak field ligand. Halide ion is a weak field ligand and it is unable to halide ion is a weak field ligand and it is unable to pair up weak field ligand and it is unable to pair up the 3D electrons, unable to pair up the 3D electrons against the Hund's rule. So this is what you should know. See, there's some extra information you must require to solve this kind of question. Like I said, the nature of ligand is very important. You should know whether it is weak or strong ligand. Similar question, NiCO4. Okay, you need to find out the hybridization, number of unpaired electron, magnetic properties, and geometry. I'll give you one information here that CO, carbon atom, is the donor and it is a strong ligand. Try to do this. See, I'll tell you first of all, since CO is a neutral ligand, so oxidation state is what? 0 of metal, Ni. Draw the similar thing you do, and you let me know just the hybridization of this, number of unpaired electron, magnetic behavior, and geometry. 2 minutes. You try this, and then we'll discuss. Quickly. Last question for today. Done. Tell me. What is the answer? Hybridization, tell me. D2sp, how it is possible? D2sp is not possible. I'll tell you. See, the oxidation state is 0, and the electronic configuration of nickel, which is 28 electron, is nothing but argon, then 4s2, 3d8. Orbital diagram is what? First of all, we'll draw 3D, which is 1, 2, 3, 4, and 5. And then we'll have 4s, and then we'll have 4p. Okay, this is 3D, 4s, and 4p. So 3D has how many electrons? 8. And Cu is a strong ligand. Okay, so what happens here, you see, first of all, the electron will be like this: 1, 2, 3, 4, 5, 6, 7, 8, and 4s2 has 2 electron. Okay, now what happens, since it is a strong ligand, so this electron, there will be rearrangement of electron. Okay, okay. There will be rearrangement of electron and against the Hund's rule, correct? This 2 electron actually, which is there in 4s orbital, it jumps into the 3D orbital like this and pairs up these electrons since the ligand is strong. So actually what happens, this I have written like this to make you understand, but actually this won't follow Hund's rule at all. We'll have orbital like this: 1, 2, 3, 4, and 5, and 3d8 if I am considering, then it will be like this: 1, 2, 3, 4, 5, 6, 7, 8. Like this they'll fill. It's not like that: 1, 2, 3, 4, 5, 6, 7, 8. It won't happen like this. So actual thing is this, because this electron jumps over here, directly pairing of the electron takes place. This is for you to understand. So all these electron goes into d subshell only, and the final configuration of this will be something like this: 1, 2, 3, 4, and 5, and each of these orbital has 2 electron. 4s will be empty, 4p will be empty, right? So this 4s 4p, because again the coordination number is 4, so they require 4 vacant orbital, which takes part into hybridization and forms 4 sp3 hybridized orbital here. So again, the hybridization is what? sp3. Geometry is what? Tetrahedral. Since all the electrons are paired, you see here, magnetic properties, diamagnetic, and number of unpaired electron is what? Number of unpaired electron is 0. sp2d, there is no d orbital. You see, Shreya, where is the d orbital? We have d orbital here, but we required only 4 orbitals, which is 1, 2, 3, and 4. So it won't go beyond this. The 4 lowest energy orbital takes part into hybridization always. Got it? Any doubt, guys? All of you understood? Correct. Okay, so we'll start from here in the next class. Okay, we have to do so many examples in this because this is the important part of this chapter we have. So we'll do next some more example on coordination number 4, then 5 and 6 will finish, and then we'll move on to the crystal field theory, where we'll understand which ligand is weak or is strong. Okay. Okay, thank you. We'll see you in the next class. Bye bye. Take care.